Good morning to all. As per the instructions of Commissioner of Collegiate Education, Telangana State, we, the faculty of government degree colleges, are doing video classes and uploading in YouTube. I, D. Lata, lecturer in mathematics, Government Degree College, Armoor, is now going to take the video lesson on the topic rank nullity theorem. Rank nullity theorem is the topic in theorem in matrices. The statement of rank nullity theorem. If A is any matrix, then the row space and column space have the same dimension. This is the statement of rank nullity theorem. Once again, let us look into the statement. If A is any matrix, then the row space and column space of A. Already in the last video, we have discussed about the row space, column space and their basis for any matrix. Now, in this theorem, there is one new terminology, that is dimension. Dimension is nothing but the number of elements in any basis. Already, we know how to find the basis of row space and also the basis of column space for any matrix. So, after finding the basis for the row space, if we count the number of elements in the basis, that will give the dimension of the row space. Similarly, after finding the number of elements in the column space, then the number of elements in the column space of the basis of A, then you will get the dimension of the column space of A. And this rank nullity theorem says that the dimension of the row space of any matrix and the dimension of the column space of any matrix is the same. Now, using that definition, using that statement, we are going to look into the definition of it. The common dimension of the row and column space of a matrix A is called the rank of A, and it is denoted by rank A. It's also sometimes denoted by row A. And the dimension of the null space of A is called the nullity of A and is denoted by mu of A. Actually, it's denoted by mu of A. So, now we are discussing about the definitions of rank and nullity, because the topic which we are going to deal is rank nullity theorem. So, we need to know what is rank and what is nullity. Then only we can relate those two terms and state the theorem, rank nullity theorem. So, what is rank? Let us look into what is rank now. The common dimension of the row and the column space of a matrix is called the rank of A. So, the dimension of the row of a matrix or the dimension of the column of the matrix are same. That's what we have discussed in the last slide. Now, we are saying that that common dimension is called rank, and the dimension of the null space, actually null space is the solution set of the matrix. So, the dimension of that null space is called nullity of A, and usually rank of A is denoted by row of A and nullity of A is denoted by mu of A. So, finally, we have learned what is meant by rank and what is meant by nullity. What is rank? Rank is nothing but the dimension of either row space or column space, because the dimension will be same for the row and also column. And nullity is nothing but the dimension of null space of A. Now, here is one example finding the rank and nullity of a 4 by 6 matrix, 4 rows and 6 columns in that matrix. Okay, let us look into the problem. Find the rank and nullity of the matrix A equal to, this is a 4 by 6 matrix. So, I am going to read row wise. There are 6 columns row wise. First row, -1, 2, 0, 4, 5 and -3. Second row is 3, -7, 2, 0, 1 and 4. Third row is 2, -5, 2, 4, 6, 1. The last row is 4, -9, 2, -4, -4 and 7. The big matrix, 4 by 6 matrix. Now, we are going to find the rank and also nullity of this given 4 by 6 matrix. To find the rank of the matrix, we have to first find the basis of either row space or column space. Suppose we are going to find a row space. To find the basis for either row space or column space, first of all, the given matrix must be reduced to echelon form. So, the given 4 by 6 matrix is now going to be reduced to echelon form. Echelon form is using the first row, first column element, we will make all the elements below that in that first column as 0. Next, we will consider the second row, second column element, and using that all the elements below and above are made 0. Next, using third row, third column element, the elements below and above in the third column are made 0. Next, considering the fourth row, fourth column element in the matrix, we will make all the other elements in the fourth column as 0. So, for this type of echelon form, usually we will go for row operations, because even though you perform row operations, there won't be any change in the solution set of the matrix of the homogeneous system of equations Ax is equal to 0. So, while trying to reduce that in the echelon form, we will get third row and fourth row elements all as 0 for this particular problem. For this particular problem, by operating second row, third row and fourth row by using first row, and first row, third row and fourth row by using second row, second column element, and by operating first row, second row and fourth row by using third row, third column element, and by using fourth row, fourth column element, first, second and third row changes, the echelon form has become, or now is in the form of 1, 0, minus 4, minus 28, minus 37, 13. And the second row in the row echelon form is 0, 1, minus 2, minus 12, minus 16, 5. And the third row, total 0 elements. Fourth row also, total 0 elements. That means in this 4 by 6 matrix, only 2 non-zero rows are existing and total 2 zero rows. So, as there are 2 non-zero rows in the row echelon form thus obtained from A, the row space and column space will be both of 2-dimensional. That means the number of elements in the basis of the row space of the given matrix 4 by 6 will be 2. Because there are 2 elements in the basis of the row space of the matrix, we say that the rank of the given matrix is 2. Okay. So, you have to take one paper and pen and then try to solve this echelon form so that you will get clear how the row elements are becoming 0 and how non-zero rows are existing. With that only we can conclude a rank of A. Now, to find the nullity. Nullity of the matrix is nothing but the solution set of the matrix. Because it is a 4 by 6 matrix, definitely 6 variables will exist. We name those 6 variables as x1, x2, x3, x4, x5 and x6. So, the 6 variables are named starting from x1 to x6. And the matrix now obtained in row echelon form is written as an equational, is converted to equation form because there are only 2 rows. Therefore, you are going to get just 2 equations in total 6 variables. 2 equations in 6 variables. What are those 2 equations? Let us see. So, in the row echelon form, from the non-zero first row, by allotting x1 to x6 variables, and these first row elements are treated as their coefficients, the equations will be x1 plus 0x2 minus 4x3 minus 28x4 minus 37x5 plus 13x6 is equal to 0. And the second equation will be 0 into x1 plus x2 minus 2x3 minus 12x4 minus 16x5 plus x6 is equal to 0. So, just 2 variables in, just 2 equations for 6 variables. So, from these 2 equations, you have to take the solution set for x1, x2, x3, x4, x5 and x6 because 2 equations for 6 variables is an inconsistent system. We are treating x3 as R, x4 as S, x5 as T and x6 as U. with this substitutions, from the two equations, we get x1 as 4r plus 28s plus 37t minus 13u. That is from the first equation. And with the same substitution, the second equation will give you x2 is equal to 2r plus 12s plus 16t plus 5u. So, with this x3 is equal to t, x4 is equal to s, and x3 is equal to r, x4 is equal to s, x5 is equal to t, and x6 is equal to u. The variables x1, x2, x3, x4, x5, x6 has the solution set as r into, from the first equation, x1 is equal to 4r. So, r into 4 plus s into 28 from second equation. From first equation, r into 4, second equation 2, third equation 1, x3 for x3 you are taking r coefficient as 1, and x4, x5, x6 don't have r. Therefore, r into column matrix 4, 2, 1, 0, 0, 0 plus s into the coefficients of s from x1, x2, x3, x4, x5 and x6 is 28, 12, 0, 1, 0, 0 plus t into the coefficients of x3, the coefficients of t from all the 6 equations, 37, 16, 0, 0, x5 there is 1 and 0 plus u into, again from all the 6 we get minus 13, minus 5, 0, 0, 0, 1. So, the null space is nothing but the set consisting of 4 elements, that is 4 column matrices. First one is 4, 2, 1, 0, 0, 0. And second one is 28, 12, 0, 1, 0, 0. Third one is 37, 16, 0, 0, 1, 0. And finally, the fourth one is minus 13, minus 5, 0, 0, 0, 1. Therefore, the null space of the given matrix 4 by 6 has 4 elements. Therefore, the dimension of the null space is equal to 4. And ultimately, the nullity of A is equal to 4. So, hence, for the given matrix A, which is of a 4 by 6 order, rank is 2 and nullity is 10. Sorry, nullity is 4. Rank is 2, nullity is 4. Our theorem says that if you consider any matrix, then the rank of A is equal to rank of A transpose. In the last video, we have proved this point in the example. For a given matrix, we have considered A transpose, and for that A transpose, after finding the row space, we have concluded for column space. So, for any matrix A, if you calculate the rank, then for A transpose also, we get the same rank. Therefore, rank of A is equal to rank of A transpose, where A is any matrix. Now, if A is a matrix with n columns, then by the rank nullity theorem for matrices, rank of A plus nullity of A must be equal to n. So, that is n means the number of columns. The number of columns. If A is a m by n matrix, then rank of A is equal to the number of leading variables in the solution of Ax is equal to 0. Rank of A is equal to the number of leading variables in the solution of Ax is equal to 0. And nullity of A is equal to the number of parameters in the general solution of Ax is equal to 0. So, whenever A is a m by n matrix, then rank of A is equal to the number of leading variables in the solution of Ax is equal to 0, and nullity of A is equal to the number of parameters in the general solution of Ax is equal to 0. That number of parameters means the number of elements in the basis of a null space. Ax is equal to 0. Now, let us look into the example 2. The sum of rank and nullity. Suppose the matrix A is considered. The matrix A is equal to, first row, -1, 2, 0, 4, 5, -3. Second row is 3, -7, 2, 0, 1, 4. Third row is 2, -5, 2, 4, 6, 1. Fourth row is 4, -9, 2, -4, -4, 7. Again, this is a 4 by 6 matrix. Therefore, the number of columns is equal to 6. And this for the same matrix, in the last PPT, we found the rank. The rank of A is nothing but the number of elements in the basis of row space or the dimension of the row space. Of course, it is nothing but the dimension of the column space or the number of elements in the column space in the basis of the column space. And in the previous PPT, we found that the row space of A consists of 2 elements. Only 2 rows are non-zero rows. All the remaining 2 rows are 0 rows. Therefore, the basis of row space is equal to 2. The number of elements in the basis of row space is equal to 2. That means rank of A is equal to 2. And the nullity of A is the number of variables. Nullity of A is nothing but the dimension of the null space or the number of elements in the basis of null space of the given matrix. So, the number of elements in the basis is 4. We got for the same problem null space consisting of 4 elements. The basis of null space consists of 4 elements. Therefore, nullity of A is equal to dimension of the null space is equal to 4. Thus, rank of A is equal to 2 and nullity of A is equal to 4. Therefore, when you add rank and nullity, rank of A plus nullity of A is equal to 2 plus 4, that is 6. 6 is nothing but the number of columns in the given matrix, because the given matrix is a 4 by 6 matrix. We have 4 rows in the given matrix and 6 columns in the given matrix. That is, the number of columns is equal to 6. In general, if A is an m by n matrix, suppose if A is an m by n matrix, the number of columns will be equal to n. Therefore, rank of A plus nullity of A is equal to n is the generalized statement. Row of A plus mu of A is equal to n is the generalized statement. And here we have concluded in proving that rank of A and nullity of A is equal to the number of columns of the given matrix. Indirectly, it is the proof of the rank nullity theorem. That is, it's an example for a rank nullity theorem. This material and the theorems, problems, everything are collected from the textbook of Vector Calculus and Linear Algebra, which is published by Atal Publications. So this book is treated as the reference textbook for this rank nullity theorem. So you please refer this textbook of Vector Calculus and Linear Algebra by Atal Publications. And this is only for academic purpose, not in commercial way. And I thank you all. You please go through the row space, column space, null space, and then refer the dimension definitions, that is rank of A and nullity of A, and finally conclude with the rank nullity theorem and its problems for verification. Thank you one and all.